So for section 1.2, we have limits and continuities of functions of several variables. So I expect that you have watched the associated lecture videos. And for the discussion today, I'll just answer the problems I have prepared in relation to this topic. So let's start with our first problem here. Determine if this function f of xy, which is a piecewise function given by this expression here, okay, is continuous at the point x comma y, which is square root of 2 comma 1. And then if not, classify the type of discontinuity. So our piecewise function f, it is defined as x squared minus 2y squared all over y minus square root of x squared minus y squared if the point x comma y is not square root of 2 comma 1. Otherwise, if we are looking at the point x comma y equals square root of 2 comma 1, the value of the function f is equal to 2. Okay? So what do we have in here? You have square root of, on the denominator, you have this square root thing, and what's inside is x squared minus y squared. Okay? And also we have y minus this square root of this guy here. So what is in this function is that, of course, this x squared minus y squared, we want this to be greater than 0, greater than or equal to 0. And furthermore, we don't want y minus square root of x squared minus y squared to be 0. Okay? So we have some restrictions if we are going to ask what the domain of the function f is. Okay? But anyway, let us look at the continuity of this function at this point, square root of 2 comma 1. So how do we do this? Normally, proving that a function with several variables is continuous is harder than proving that it is discontinuous at some point. So in your lecture, you were given a technique on how to show that a certain function with several variables is not continuous. You get maybe two or three paths passing through the point in discussion. Okay? So we will try to get a path that passes through square root of 2 comma 1. And then we will show that maybe the limit or may exist or may not exist. Okay? If the limit exists along that path, we will find another path. Okay? We will try to use another path and find the limit of the function. Okay? As the point x comma y goes to the point square root of 2 comma 1. And then we hope that with these two different paths, there will be different limits. And once we have obtained the different limits, okay, then we can conclude that the function is not continuous. Correct? So that's what we're going to do. Solution. So maybe let us consider the path. Let us start with the path x equals square root of 2. Okay, so along the path x equals square root of 2, let me move it here. Okay, and therefore what do we have? Since we are fixed, we have fixed x equals square root of 2, then we will just let y approach 1. Correct? So in here, we have the limit of f of x, comma y, as the point x comma y goes to the point square root of 2 comma 1. But then again, since we have fixed, okay, we have fixed the line where our point will pass through, okay, or will move along. We have here, we will change this into the limit of f of square root of 2 comma y as y tends to 1. So our idea is to reduce the limit problem into a limit of functions with a single variable. Correct? Now, since your y is just approaching 1 and it may not be equal to 1, in fact, we don't want y to be equal to 1, it means the x comma y or square root of 2 comma y still satisfies this condition here. Okay? So, for this expression, we will replace our x. Okay, we will replace our x with square root of 2. So we will have the limit of square root of 2 quantity squared. And then the y, it's still the variable y. So we have 2y squared divided by y minus square root of 2 quantity squared minus y squared. And here we have y approaches 1. So the problem is much simpler than the first here. Let us simplify all the things here. We have the limit as y approaches 1. Then we have 4 minus 2y squared over y minus square root of 4 minus y squared. Okay? And why is it 4? It should be 1. Here, it should be 2, I mean. Okay? So as y tends to 1, okay, this will be 4 minus 2 times 1. And then on the denominator, we'll have, why is this 4? This should be equal to 2 also. This should be equal to 2 also. So we will have here 2 minus 2 times 1. So that's 2 minus 2 in the numerator. It is equal to 0. Okay? It's equal to 0. And then on the denominator, we will have 1 minus square root of 2 minus 1. So 1 minus 1 on the denominator. So this is equal to 0. So here we have 0 over 0. We can maybe simplify this expression so that we can cancel an expression, the y minus 1 in both the numerator and denominator. Or since this is 0 over 0, we can just apply L'Hopital's rule. So if we apply L'Hopital's rule, okay, so equals. So by L'Hopital's rule, we will have the limit as y tends to 1. The numerator will just have negative 4y. On the denominator, we will have 1 minus derivative of square root of 2 minus y squared. So you will have, so try to check. You should get minus y over square root of 2 minus y squared. Okay? So look at this. As y approaches 1, the numerator, it's non-zero. So at least we will have some answer, either a number or does not exist. Or okay, so either we'll get a limit, which is a number, or the limit won't exist, depending on the value of the denominator. But as you can see, if we evaluate y equals 1, okay, we'll just have -4 in the numerator. On the denominator, this is minus and then this is minus, it becomes plus. So we will have 1 plus 1 over denominator, it's square root of 2 minus 1. So this is equal to what? -2. So at least we got some value for the limit. Okay? So this is along x equals square root of 2. Now, look at this. At the evaluation, okay, at the evaluation, square root of 2 comma 1, the value of f is equal to 2. And this is already -2. What does that mean? The function is already not discontinuous, not continuous. Correct? Okay? Therefore, we have answered that the function is not continuous. Yeah? Now, suppose let us check the line maybe along y equals 1. Okay? Suppose we check the line y equals 1. So the original problem, we will have the limit of f of x comma y as x comma y approaches square root of 2 comma 1. Okay? Since we are moving along y equals 1, we can replace this as the limit of f of x comma 1. And here, we just have to let x approach square root of 2. So again, if we now substitute our function, so your y is equal to 1, your x only approaches square root of 2. So it still satisfies this condition, and therefore we have this function here. So we have the limit as x approaches square root of 2. In the numerator, we will have x squared minus 2 divided by, you have 1 minus square root of x squared minus 1. And as x approaches square root of 2, notice this will be 0 over 0 again. Okay, try to check. This is still 0 over 0. We apply L'Hopital's rule. So this will be the limit as x approaches square root of 2. Okay. We get derivative of the numerator. It's just 2x. We get derivative of the denominator. This is negative. So what is this? Negative square root of, well, negative x over square root of x squared minus 1. Okay? And as x approaches square root of 2, we will have here, well, you can rewrite this expression here. Okay? Let us try to rewrite this expression here. If we do that, we will have the limit as x approaches square root of 2. We'll just have negative 2 times square root of x squared minus 1. Okay? The x will cancel this x here. The x in the numerator will cancel the x in here. That's why we will get this. Okay? And if you try to calculate this, you will still get what? Negative 2. So now, look, the limit of the function along this line, it's equal to -2, the limit of the function along this line is also equal to -2. Maybe the limit is actually -2 along any possible lines or any possible curve. So let us try to show that indeed the limit of this function along any possible curve is equal to -2. So this will be our approach. So let's write here continuation. So we want to find the limit of f of x comma y as the point x comma y approaches square root of 2 comma 1. So let us write the function. We have the limit of x squared minus 2y squared over y minus square root of x squared minus y squared as the point x comma y approaches square root of 2 comma 1. So what we're going to do is to multiply both the numerator and denominator by the conjugate of the denominator. So we multiply and both the numerator and denominator by y plus square root of x squared minus y squared. Then also denominator y plus square root of x squared minus y squared. So if we simplify this, we will have the limit as the point x comma y approaches square root of 2 comma 1. In the numerator, let us just write them in factored form. So here you will have x squared minus 2y squared times y plus square root of x squared minus y squared all over. In the denominator, difference of two squares, so we will have y squared minus quantity x squared minus y squared. If you calculate this guy here, this is simply 2y squared minus x squared. And you have here x squared minus 2y squared. So we can just cancel this guy here with this guy, and we will be left with -1. So what I'm saying is the expression will be simplified to negative of y plus square root of x squared minus y squared. And we have the point xy approaching square root of 2 comma 1. And in here, we clearly see that this is just negative of 1 plus square root, or 1 plus square root of square root of 2 squared minus 1 squared. So this is equal to -2. So indeed, the limit of the function as the point xy approaches square root of 2 comma 1 is equal to -2. So as a conclusion, therefore, f is discontinuous at the point square root of 2 comma 1. The discontinuity is removable. The discontinuity is removable.